You are floating now, suspended in an impossibly vast darkness. There is no sound here, only the profound quiet of space itself, a silence so complete that it has texture, weight, presence. Around you, dust particles drift in slow motion, each one barely visible in the faint light of distant fires still being born somewhere in this endless night. The air itself is thin, almost unreal, and if you could see your breath, it would crystallize before your eyes, hanging frozen in the void. This is the space between worlds. This is where stars live their long, patient lives. Feel the weightlessness settling into your bones. Feel the cold embrace of infinity itself, a coolness that is almost gentle. Feel how still everything is, how quiet, how alone. Somewhere in the cold depths of space, a cloud drifts. It has been drifting for millions of years already, and it will continue to drift for millions more. This cloud is vast beyond comprehension. It stretches across distances so great that light itself would take 200 years to cross it, and yet within this immensity, something is beginning to change. The cloud is a stellar nursery, a place where new stars are born, though the birth happens so slowly that no single moment marks a beginning. There is only the gradual gathering, the patient accumulation of matter into something that will one day ignite and shine. Within the cloud, gravity works ceaselessly. Imagine gravity as an invisible current, so gentle that no sensation announces its presence, yet so persistent that it cannot be resisted. It draws particles together with a pressure so subtle that you would never notice it in a single moment, yet across millions of years, this pressure becomes irresistible. A region of the cloud, slightly denser than the rest, begins to pull material toward itself. More dust accumulates. More hydrogen drifts inward. The cloud begins to rotate, ever so slightly, as if slowly spinning in place. This rotation accelerates gradually, much as a dancer spins faster when drawing in their arms, though the time scale here is measured in millions of years. The cloud within which a star is forming is extraordinarily cold. The temperature hovers just above absolute zero, only 10 degrees above the lowest temperature possible in the universe. And yet within this profound cold, the cloud possesses a kind of hidden richness. Carbon and oxygen molecules drift through the darkness. Grains of silicon and ice coat themselves in layer upon layer of frozen material, building themselves grain by grain into tiny sculptures of solid matter. This frozen tapestry will eventually become something magnificent, planets, perhaps, or the building blocks of worlds yet to be imagined. As decades and centuries and millennia accumulate into millions of years, the gathering continues. The material at the center of the rotating cloud becomes increasingly concentrated, pressed inward by gravity on all sides. The disk of material around this center flattens and thickens. Denser material settles toward the middle, while lighter elements are pushed toward the edges. The rotation becomes more pronounced, the spiral more pronounced, and within this disk, smaller concentrations of matter begin to form, seeds of what will eventually become planets, though their story lies beyond our journey into this particular star's solitude. Within the dark nebula, the protostar, the star-to-be, continues its patient transformation. The material at its center is being compressed by the weight of all the material surrounding it, and as this compression increases, something unexpected begins to happen. Heat emerges from this pressure. The temperature rises gradually, degree by degree, each increase imperceptible but accumulated across centuries into something profound. The temperature climbs from the initial 10 Kelvin. Higher and higher it rises, crossing 100 million degrees, then 200 million. The protostar begins to glow with infrared light, heat radiation that human eyes could never perceive, but that specialized instruments would see as brilliant fire. The disk around the young star continues to spin, and occasionally, jets of material shoot outward in spectacular streams, though their speed would still seem gentle compared to the catastrophes that occur elsewhere in the cosmos. For hundreds of thousands of years, the protostar remains largely hidden within its cocoon of dust and gas. The light it produces cannot escape the surrounding cloud. It is absorbed and re-radiated back inward, trapping the heat, pressing the core hotter still. The temperature continues its inexorable climb. 300 million degrees, 400 million. The pressure in the core becomes so great that it seems it must explode. And yet the weight of all the material above it holds it in place, compressing it ever further. And then, after perhaps 1 million years of patient gathering and heating, something profound occurs. The temperature in the core reaches a threshold, approximately 10 million Kelvin, and at this moment, something awakens. Hydrogen nuclei, stripped of their electrons and moving at tremendous speeds, begin to collide with one another. When they collide at this temperature, something happens that seemed impossible. They stick together. They fuse. They merge into helium. This fusion releases energy, vast amounts of energy. And this energy creates an outward pressure that balances the inward crush of gravity. The star has been born, yet this birth passes entirely unmarked by fanfare or drama. The star does not suddenly burst into brilliance. Instead, its brightness gradually increases as the fusion process becomes more efficient, more established. The surrounding cloud of dust that has swaddled it begins to clear, dispersed by the star's radiation and by the stellar wind, streams of charged particles flowing outward from the star's surface like an invisible breath. Within a few million years, the young star stands revealed, shining steadily in the darkness. It is now what astronomers call a T-Tauri star, a young stellar object still burning with the vigorous energy of youth, still surrounded by the disk of material that spirals inward, feeding occasional waves of matter to its surface. If you could witness this newborn star directly, you would see something turbulent and alive. Its luminosity flickers and varies as material from the disk crashes onto its surface. Its rotation is rapid, perhaps once every few days, making its surface writhe with activity. Prominences of hot plasma arc above the surface into the surrounding space like the fingers of a dreaming hand. The solar wind is fierce and powerful, a constant stream of particles being blown away, capable of sweeping away any remaining loose material in the surrounding nebula. And yet, despite this apparent turbulence, the star has entered the phase that will define most of its existence. The main sequence, a period of stability and quiet burning that will last for billions of years. Move with us now, forward in time, past those first turbulent millions of years, into an age of remarkable stability and quietude. Our star, let us imagine it much like our own sun, a medium star with a mass of 1 solar mass, has settled into what we might call peaceful middle age. The violent processes of its youth have long since calmed. The surrounding disk has either become planets and smaller bodies or been swept away entirely. The star's rapid rotation has gradually slowed, and now it turns on its axis once every 30 days, a leisurely pace compared to its frantic youth. Within the star's core, hydrogen continues to fuse into helium with methodical precision. This process has become the heartbeat of the star. 4 hydrogen nuclei merge to become 1 helium nucleus, and in this merging, a small amount of mass is converted entirely into energy according to the relationship that Einstein discovered. Energy equals mass times the speed of light squared. This energy, released at the core, slowly diffuses outward through layers of material, traveling at a pace so leisurely that it requires 200,000 years to journey from the core to the surface. A photon created at the center of the star will bounce countless times, trillions upon trillions of times, before finally emerging into space, a random walk through dense plasma that takes 200 millennia to traverse a distance that light could cross in seconds if it moved in a straight line. The star maintains a perfect equilibrium, a balance between 2 opposing forces locked in eternal embrace. Gravity, with its inexorable inward pull, seeks to collapse the star further, to compress it into an ever smaller volume. But the energy released by fusion creates an outward pressure, a pressure from radiation and from the heated gas that pushes back against gravity's squeeze. Like breath and heartbeat, the star inhales and exhales in perfect rhythm. If the core temperature were to rise even slightly, the fusion rate would increase, creating more outward pressure and causing the star to expand slightly, which would cool the core and slow the fusion. If the core were to cool, the fusion would decrease, allowing gravity to compress the star slightly, heating it up and increasing fusion once more. It is a self-regulating system of extraordinary elegance, born not from intention, but from the fundamental laws of physics itself. The star's surface settles at a comfortable temperature, approximately 5,778 Kelvin, giving it a pale yellow color that seems almost welcoming, almost kind. Its luminosity stabilizes at what astronomers call 1 solar luminosity, enough power to sustain life on a planet orbiting at just the right distance. The years accumulate into centuries, centuries into millennia, millennia into millions of years. The star continues its quiet work, largely unchanged in appearance. It has entered its main sequence lifetime, and for a star like this phase will endure for approximately 10 billion years, a span of time so vast that it nearly encompasses the entire age of the universe itself. As we turn our attention outward from the star to the space surrounding it, we begin to appreciate the profound solitude of stellar existence. The nearest star to our Sun is Proxima Centauri, and it lies at a distance of 4.24 light-years away. Light, traveling at the fastest speed possible in the universe, requires 4 years and 3 months to journey from Proxima Centauri to our Sun. If you were to stand on a world orbiting our Sun and look up at Proxima Centauri, the light entering your eyes would have begun its journey when you were 4 years younger. To comprehend this distance in simpler terms, the distance from Earth to the Sun is approximately 150 million kilometers. Proxima Centauri lies at a distance of approximately 40 trillion kilometers. If you were to drive to Proxima Centauri at a modest highway speed of 100 kilometers per hour, the journey would require 46 million years. the entire recorded history of human civilization, roughly 5,000 years, would represent only 0.01% of this journey. And yet Proxima Centauri is the nearest star. In the neighborhood of our Sun, within a sphere extending 10 light-years outward in all directions, there are perhaps 30 to 40 known stars. 30 to 40 islands of light separated by vast seas of cold, empty space. Beyond this sphere, the stars continue to thin out gradually, though they never disappear entirely. The galaxy stretches across 100,000 light-years and contains between 100 billion and 400 billion stars, depending on what astronomers observe today. Yet within all this multitude, each star exists in profound solitude. Our Sun has no companion star orbiting it, no binary dance with another sun. It exists alone. Its solitude is complete and perfect. The nearest star is so far away that the Sun's gravity barely affects it. The light from the Sun does not reach Proxima Centauri at a brightness comparable to the light the Sun receives from nearby stars. In the sky of the Sun, if the Sun could somehow perceive the stars around it, those stars would appear as isolated points of light, separated by endless gulfs of darkness. And yet, despite this apparent isolation, the Sun's path through space is subtly shaped by all of these distant stars, by their combined gravity creating the large-scale structure of the galactic field through which all stars drift. The stars themselves, despite their appearance of being fixed and eternal, are not stationary. They move through space with velocities of 10 to 30 kilometers per second, following orbits around the galactic center that take hundreds of millions of years to complete. Our Sun moves through space at approximately 20 kilometers per second, carrying with it all the planets of our solar system, all the asteroids and comets that orbit it, in a journey that has been continuing for 4.6 billion years and will continue for billions more. The Sun's orbit around the galactic center is not a perfect circle, but rather a nearly circular path with subtle variations. It moves through the galaxy's structure, passing through regions of higher and lower density. Approximately every 230 million years, the Sun completes one full orbit around the galactic center, a period sometimes called a cosmic year. In that time, the Sun travels approximately 230 million light-years through the galaxy. The last time the Sun was at this point in its orbit, the dinosaurs had not yet evolved. The Earth was a different world, with continents arranged in configurations unrecognizable to modern eyes. As the Sun moves through the galaxy, the stars around it appear to shift position gradually, so slowly that the changes are barely perceptible across a human lifetime. This motion, while real and continuing, feels almost imperceptible. A star might move across the sky by an amount equal to the diameter of Earth as seen from the Sun, a tiny shift that would require 1 million years to become noticeable to the unaided human eye. And yet across billions of years, these motions become profound. The configuration of stars in the Sun's neighborhood billions of years in the future will be unrecognizably different from the configuration today. Stars that are currently nearby will drift away. Stars that are currently distant will gradually approach, though never coming close enough to threaten collision. This slow drift through space is the normal condition for all stars. They are not locked in place, but are instead moving with constant velocity through the three-dimensional space of the galaxy. their motions determined by where they were born and how the galactic environment has shaped their paths. The Sun, on its current trajectory, will never collide with another star. Such direct encounters are extraordinarily rare because the distances between stars are so vast relative to their sizes. But through the gentler tug of gravity, the Sun's path has been shaped by the stars around it, by the overall distribution of matter in the galaxy, by the massive black hole at the galactic center, which sits approximately 26,000 light-years away and whose gravity, attenuated by distance, subtly influences the Sun's long-term trajectory. Let us turn our attention inward now, to the deep interior of our star, to understand in gentle terms the process that sustains it across its billions of years of stability. The Sun's core reaches a temperature of approximately 15.7 million Kelvin, a heat so intense that it seems inconceivable. And yet this temperature is barely sufficient for hydrogen fusion to proceed at the rate necessary to maintain the Sun's luminosity. At the star's heart, hydrogen nuclei dance and merge in an ancient rhythm. The process happens so slowly that billions of collisions are required for a single successful fusion event, a process so rare that it might seem it could never sustain a star. And yet the sheer number of nuclei in the star's core, more than 10 to the 56 hydrogen nuclei, is so vast that rare events become commonplace. When nuclei collide and merge, they fuse into heavier elements, and in this merging, energy is released. This is the fundamental fire that sustains the star, the process that has been burning continuously for billions of years and will continue for billions more. This energy is generated at a rate of approximately 383 billion megawatts, a quantity almost beyond comprehension. And yet it is distributed across the entire volume of the Sun's core, so the power density is not as extreme as one might imagine. The energy generated at the core slowly diffuses outward through layers of increasingly cool material. In the core, and in a zone extending perhaps 1/3 of the way to the surface, energy travels primarily through radiation, photons being absorbed and re-emitted countless times as they work their way outward, much like light traveling through a vast maze of mirrors, bouncing endlessly toward the surface. Above this radiative zone lies the convective zone, where energy is carried outward by the bulk motion of heated plasma rising from below and cooler material sinking from above, a process much like convection in a pot of heating water. The journey from the core to the surface is extraordinarily slow. A photon created at the core does not travel in a straight line to the surface. Instead, it is absorbed and re-emitted countless times, bouncing between atoms in a random walk, so that a photon generated at the Sun's core requires approximately 200,000 years to reach the Sun's surface. This journey, measured in quadrillions of bounces, speaks to the profound density and thickness of the star's material, to the slow and patient way that energy must travel through matter. And so we find ourselves contemplating one of the fundamental facts of stellar existence: the extraordinary span of time across which a star like our Sun maintains its stable, quiet burning. 10 billion years, a period so vast that it encompasses nearly the entire age of the universe itself, which is approximately 13.8 billion years old. The Sun is currently approximately 4.6 billion years into this main sequence phase, meaning it is roughly halfway through its stable lifetime. For another 5.5 billion years or so, the sun will continue to shine much as it does now, providing the steady energy that sustains whatever worlds orbit it. 4.5 billion years is so vast that it completely dwarfs the timescales of human experience. Modern humans have existed for perhaps 200,000 years, a span so brief that it represents only 0.004% of the sun's main sequence lifetime. Recorded human history spans merely 5,000 years, and yet the sun is only halfway through. For another 5.5 billion years yet to come, it will continue to burn. This stability is not perfect, however. Over billions of years, as hydrogen fuses into helium in the core, the composition of the core gradually changes. The core becomes progressively richer in helium and progressively poorer in hydrogen. These subtle changes accumulate into noticeable effects. The sun is brighter now than it was when it first reached the main sequence. 4.5 billion years ago, when Earth was first forming, the sun's luminosity was approximately 70% of its current brightness. A difference that seems modest until we consider its implications. If the sun were truly only 70% as bright in the Earth's earliest days as it is now, the Earth would have been almost entirely frozen in ice, receiving insufficient heat for liquid water to exist on its surface in great quantity. And yet we know from the geological record that liquid water existed on the early Earth, that oceans covered much of the planetary surface, that life emerged and began evolving into increasingly complex forms. This apparent paradox is resolved by understanding that the early Earth's atmosphere was different from the modern atmosphere, containing higher concentrations of greenhouse gases, methane, carbon dioxide, water vapor, that trapped the sun's heat more effectively, keeping the surface warm despite the sun's lower luminosity. Over billions of years, this situation has balanced itself. The sun has gradually brightened, and the early Earth's greenhouse-heavy atmosphere has gradually become more oxygen-rich, with methane and other potent greenhouse gases being removed through various processes. The balance between the sun's gradually increasing luminosity and the gradually decreasing heat-trapping capacity of the atmosphere has allowed the Earth to maintain relatively stable surface temperatures across this vast span of time, though not without fluctuations and variations, including ice ages and warming periods. Many main sequence stars like our sun are accompanied by planetary systems, collections of worlds that share the star's journey through space and time. Our sun possesses 8 major planets along with countless smaller bodies, asteroids, comets, dwarf planets, and moons. All of these worlds were formed from the same disk of material that surrounded the sun in its youth, and they have evolved alongside the sun throughout its entire history. The terrestrial planets, Mercury, Venus, Earth, and Mars, are rocky worlds relatively close to the sun, each with its own character and history. Earth, by fortunate circumstance, orbits at a distance where liquid water can persist, and it possesses a moon whose gravitational influence has stabilized its rotation. These conditions have allowed life to emerge and flourish. Mars, slightly farther out, receives less solar energy. It may once have supported liquid water, but now it appears to be a cold, dry world. The gas giants, Jupiter and Saturn, orbit farther from the Sun, receiving far less solar energy, yet retaining tremendous internal heat left over from their formation. Jupiter, the largest planet, is so massive that it occasionally perturbs the Sun's motion measurably. Throughout the history of the solar system, it has served as a kind of shepherd, using its gravity to influence the trajectories of asteroids and comets. The ice giants, Uranus and Neptune, orbit even farther out in regions so cold and distant that they receive almost negligible amounts of solar radiation. Beyond Neptune lies a region called the Kuiper Belt, a disk-like collection of icy bodies and small worlds extending outward to perhaps 50 astronomical units from the Sun. Beyond even this lies the Oort cloud, a spherical shell of comets extending perhaps 1 to 2 light-years from the Sun, so distant and so thinly distributed that individual objects within it are barely understood. Yet they are all gravitationally bound to the Sun, all part of its system, all sharing in its long journey through the galaxy. This entire system, 8 major planets, countless smaller bodies, potentially trillions of comets, all revolve around and accompany a single star that itself is far from unique in the galaxy. As time drifts onward, deeper still into the Sun's quiet existence, the gradual increase in luminosity continues with patient inevitability. The core gradually becomes more helium-rich, changing how easily radiation can travel through it. The core must increase in temperature slightly to maintain the balance between gravity's inward pull and radiation's outward pressure. With a higher core temperature, the fusion rate increases, causing the star to become slowly brighter. This process is universal among main sequence stars, well understood through both theoretical modeling and observations of star clusters of different ages. Over its 10 billion-year lifetime, the Sun's luminosity will increase at an approximate rate of about 10% every billion years. Over time, the habitable zone, the region where liquid water can persist, moves gradually outward as the star brightens. Early in the Sun's main sequence lifetime, this habitable zone was located closer to the Sun than Earth's current orbit. As the Sun has brightened, the habitable zone has expanded outward. In the future, as the Sun continues to brighten, the habitable zone will eventually move beyond Earth's orbit, rendering the Earth's surface too hot for liquid water to exist. This timeline is estimated to be perhaps 1 billion years or so into the future, though this depends on various assumptions about how the Earth's atmosphere evolves. At that point, if intelligent life has not taken steps to modify the situation, the planet will gradually become uninhabitable as surface temperatures rise and the hydrosphere evaporates. For billions of years after that, the Sun will continue to shine, gradually growing brighter, until finally, approximately 5.5 billion years from now, it will exhaust its core supply of hydrogen. When the hydrogen in the Sun's core becomes depleted, the fusion process can no longer sustain the delicate balance between gravity and radiation pressure. The core, no longer supported by fusion energy from its interior, will begin to contract and heat up even more. At this point, the Sun will undergo a transformation that is almost unimaginably profound compared to its patient, stable existence across billions of years. As the hydrogen-depleted core continues to contract and heat, reaching temperatures of approximately 100 million Kelvin, conditions become so extreme that helium nuclei, which have remained inert throughout the main sequence phase, begin to undergo fusion. 3 helium nuclei combine to form carbon, a process called the triple alpha reaction. The beginning of helium fusion releases tremendous energy, and this energy causes the star's structure to respond dramatically. The outer layers expand outward, and the star becomes a red giant, a vast, bloated star with a surface that has expanded to perhaps 200 times its current radius. The red giant phase is brief compared to the main sequence phase, lasting perhaps only a few 100 million years. During this time, the star burns helium in its core, but the process is somewhat unstable. The core contracts and heats and expands and cools in subtle cycles, creating variations in the star's surface brightness. The star's stellar wind becomes increasingly fierce, and material is stripped away in great quantities. A shell of glowing gas forms around the star, expanding outward into space, illuminated by the intense radiation from the exposed core at the star's center. This shell becomes what is called a planetary nebula, though these objects have nothing to do with planets, but rather are the expelled outer layers of dying stars. As the red giant gradually sheds its outer layers, what remains is the exposed core, a tiny, incredibly dense ball of carbon and oxygen, about the size of Earth, but with a mass approximately equal to the Sun's current mass. This remnant is called a white dwarf, and it is the final state to which a sun-like star evolves. A white dwarf does not undergo nuclear fusion. It is inert, a cooling ember slowly radiating away its remaining heat into the cold darkness of space, where it will eventually fade into black, a stellar cinder drifting forever through the galaxy. And yet, even in this ending, there is a kind of quiet dignity. The white dwarf, though no longer burning, carries within it the history of billions of years of steady, reliable illumination. The elements it contains, the carbon, the oxygen, the trace amounts of heavier elements created during its fusion, will eventually be dispersed into space, scattered into the galaxy, becoming the raw material from which new stars and new planets will one day form. Nothing in the universe is ever truly lost. Everything is only transformed. The star's long life, from its quiet birth in a nebula to its patient main sequence burning to its final transformation into a white dwarf, spans approximately 10 billion years of cosmic time. For nearly all of that span, approximately 10 billion years, the star maintains its equilibrium, burning steadily, reliably, quietly. It is a life of profound stability, interrupted only at the very end by transformation. And in this lies a kind of peace, a kind of certainty that can only come from the fundamental laws of physics themselves, laws that have governed stars for billions of years and will govern them for billions more. And so, as you drift through this vast, empty space, knowing now something of the life of stars, of their patient burning and their solitude and their slow dance through the galaxy, let yourself settle deeper. The universe is incomprehensibly vast, and yet it follows patterns of such elegant simplicity that even a star's life, spanning billions of years, becomes comprehensible. Let yourself be held by the knowledge that the universe is old and patient, and that everything within it, including yourself, is made of the ashes of stars that have completed their cycles long ago. Rest now in this knowledge. Rest in the quiet. Rest in the deep, profound stillness of space itself. And